Over 1,000 new anomalies in space. Objects that were there all along, hidden in plain sight, now finally revealed by astrophysicists. And while we're still trying to understand the cosmos, we've already begun to change it. For the first time in history, humanity has deliberately altered the orbit of a celestial body around the sun. It's now official. The building blocks of life can form without water, without planets emerging freely in the cold, silent vastness of space. And this time, scientists didn't just theorize it, they watched it happen. We now have the most complete 3D map of the early universe ever created. Fragments of space debris have been transformed into a powerful new instrument for looking back in time. And from the ISS, a rare and haunting image, something never visible from Earth, a red sprite flickering at the edge of our atmosphere. These are the final 5.5 minutes of the DART probe right before impact. Moments before it struck the asteroid. The collision unleashed a violent burst of rock and dust, ejecting debris far into space. Some of it traveled astonishing distances. From afar, it looked like this. The footage was captured by a research satellite positioned at a safe distance, watching everything unfold in real time, in precise detail. For the first time, we could truly measure how the material dispersed. Based on the images, it seemed there might have been a slight push, almost like a rocket thrust. But the reality was far less certain. The data left room for doubt. And that leads to a bold, almost unsettling question. Did the asteroid's orbit around the sun actually change? At first, the goal was far more modest. To find out whether we could deflect an asteroid without explosions. No Hollywood scenario like Armageddon. No drilling, no nuclear detonation. Just pure kinetic impact. This particular asteroid was never a threat to Earth, but sooner or later, one will be. And now, a new study confirms it. We succeeded. For the first time in human history, we intentionally altered the motion of a celestial body. Strictly speaking, we altered two. The object, the probe, passed just before impact wasn't just debris, it was a second asteroid. A binary system, two bodies locked in a gravitational dance, orbiting each other. The first orbit, the one directly affected, was the smaller asteroid circling the larger one. After the impact, its orbital period shortened by 33 minutes, exactly as the mission designers had predicted. But something else happened. The violent ejection of material shifted the system's center of mass, like two dancers spinning together, suddenly pushed slightly apart. And because of that, the second orbit, their shared path around the sun, shifted as well. The change was almost unimaginably small, just 360 meters against an orbital radius of roughly 300 million kilometers. So small that detecting it required years of observations to confirm. Scientists even turned to amateur astronomers for help. People went out into fields and forests, pointing their telescopes at the night sky. In the paper, the authors thanked these enthusiasts, half-jokingly calling them not exactly amateurs. Because in practical terms, it's as if nothing moved at all. On a human scale, it would be like shifting a city the size of Rio de Janeiro by the width of a single hair. And yet, that's exactly where the breakthrough lies. Measuring and predicting changes this small was once purely theoretical when it came to asteroids. Without that level of precision, real planetary defense is impossible. Right now, we can only accurately calculate the trajectories of objects we've been tracking for years, sometimes decades. But the real danger comes from what we don't see. The Chelyabinsk meteor changed that. It forced us to take small objects seriously, to invest in detection systems, to think about early warning. Because today, even when we do spot something, we often have almost no time. Days before closest approach, sometimes less. While I was working on this video, another object was discovered already on its way. Roughly the size of a bus. It had likely passed us just weeks earlier. And with objects like these, even when we detect them, our calculations can be off by hundreds, sometimes thousands of kilometers. Which means, in the end, we're still looking up and guessing. So the authors of this new study have made a significant discovery. Astronomers have identified 43 objects in space, and while they don't yet fully understand what they are, One thing is already clear. They are anomalies. Here is an image. They suspect that at least some of these objects may be jellyfish galaxies. They're called this because they often form what look like tentacles, streams of gas carried outward from the inside, usually driven by the pressure of the intergalactic medium. Even this alone would be enough for a monumental achievement, because out of millions of possible galaxy types, scientists currently know only about 200 of this kind. And here, we have such a large addition, all at once. Perhaps this is because each of them now needs to be analyzed and verified separately. In the process, astronomers uncovered nearly 1,000 new anomalies, objects with no known counterparts. Among them, they identified two previously unknown collision ring galaxies, both discovered at the same time. And these are among the rarest cosmic creatures. This happens when two galaxies pass directly through one another, their centers colliding and sending a shockwave rippling outward, forming a glowing ring where new stars ignite and begin to form at an accelerated pace. But the funny thing is, we weren't even looking to make a discovery. It was just a nice bonus, confirmation that we're on the right track. We wanted to test a method that should allow us to find cosmic anomalies and rarities on an industrial scale, as paradoxical as that may sound. Essentially, squeezing discoveries out of junk well, these hundreds of mysterious things had been lying in plain sight for years, and nobody needed them because all the images are large and have a lot of pixels. We can't review them all. This is the Hubble Space Telescope archive, nearly 100 million images. It seems that's what neural networks are for, right? Not just for memes. But the problem is that neural networks are usually good at recognizing things that appear frequently like cats because they were trained on millions of images of cats. But if, over the entire history of observations, you have only 25 images of extremely rare objects such as protoplanetary butterfly disks, or hamburgers, as they're also called, then it's easier to pick the winning lottery numbers than to recognize these rarities in terabytes of astronomical archives. So instead of just using yet another off-the-shelf neural network, they came up with a clever algorithm, one that involves human input, but only minimally. They called it Anomaly Match. People show a few examples of the anomalies they're looking for, and then show a lot more normal objects. Like, here's the norm look. Don't mix them up. And if you do mix them up, give the frame a higher score. So, suspicious images stand out from the crowd. They score higher, and then they're rotated, flipped, and the machine has to say, "This still doesn't look normal." Then, an expert reviews not millions of images, but just the cream of the crop, the top suspects, and manually labels them. Is it an anomaly or not? This way, the model is trained very precisely and very quickly. After that, it figures out on its own what is abnormal, and, as it turns out, it does so quite well. Anomalies are interesting to astronomers precisely because they defy conventional expectations. If something is off, then why? This means there are some as yet unclear mechanisms behind it, or even laws of nature we haven't discovered yet. Here's another practical and unexpected answer to the question. Why do we need space? Viruses were taken to the ISS that turned out to be particularly effective on Earth. Scientists haven't encountered anything like this before. We're talking about well-known bacteriophages, viruses that are already well understood and extensively studied. As a reminder, they are the primary predators of bacteria, shaping microbial life across the gut, the ocean, and the soil. We've studied how they hunt on Earth in considerable detail, but how they behave in microgravity remained completely unknown. And this is especially critical in space. Based on decades of ISS observations, we know that human immune systems deteriorate in orbit, while bacteria become far more aggressive. They form stronger biofilms and develop antibiotic resistance at a much faster rate. At the same time, phages are our last line of defense against bacteria that no longer respond to antibiotics. So, in this new study, scientists wanted to understand whether it might be possible to enhance phages in space if their evolutionary partners are able to adapt as well. On Earth, A phage's greatest ally is gravity. They don't have flagella like many bacteria, so they depend on fluid movement and diffusion to find their targets. But in space, everything changes. In microgravity, like on the ISS, fluids behave differently, and movement becomes limited. If even bacteria struggle to move, what happens to phages? That was the question researchers set out to answer. They took a strain of E. coli without flagella, so it couldn't swim, and had to rely purely on chance, just like in microgravity, and placed it in test tubes with phages already present. And yes, they carefully controlled the experiment to ensure nothing was shaken or disturbed, even freezing the samples later for analysis. On Earth, within just a few hours after thawing, phage numbers in the control samples increased by a factor of 10 million, as expected. But in microgravity, after 4 hours, nothing. The scientists waited 23 days before checking again. Not 10 million, of course, but still not zero. The phage population had increased 10,000-fold. So infection does occur in space, but at a dramatically slower pace. Later, the researchers performed full genome sequencing of both the phages and bacteria from the ISS samples to understand what mutations had occurred, and the results were unexpected. Scientists had never observed such mutations on Earth. Perhaps under gravity, viruses simply don't need them. As for the bacteria, the mutations appeared mainly in genes responsible for the molecular armor on their surface, the structures that phages use to attach and inject their genetic material. This likely helped the bacteria survive for as long as 23 days in a single test tube, even under constant attack. And then came the most intriguing step. The scientists took these unusual but highly effective mutations in the phage's tail, their primary weapon, and engineered new mutant phages on Earth, now carrying select space-adapted traits. Then they unleashed them on strains of E. coli that were already immune to standard phages. This was known in advance and carefully verified. What if this happens even without water? In that case, it wouldn't be individual amino acids, but entire chains that could have formed beyond Earth, and perhaps are forming right now in places where there is no water and never has been. Which is why we wouldn't even think to look for them in those regions of deep space. These are the fundamentals of protein-based life, and it might turn out we were wrong. Anyway, they decided to test it, because so far no one has managed to either produce anything like this in a lab or observe the process in space. And theoretically, such chemistry is entirely possible. We tested it. We placed glycine in a vacuum chamber, froze it to minus 250 degrees Celsius, that is, almost to absolute zero. Then we bombarded it with protons, which fairly accurately replicates cosmic radiation. And indeed, we obtained the simplest biological dipeptide, glycyl glycine, a meaningful compound, not just some Frankenstein's monster. We verified the results using two completely different methods: infrared spectroscopy and mass spectrometry. Everything checked out. This is the first time it's been obtained. Yes, under lab conditions, but nothing that wouldn't also happen in space. Despite the beauty and persuasiveness of the experiment, it must be said that this is a preprint. That is, scientific peer review and verification by colleagues in independent experiments still lie ahead. Yes, and it's important to remember that the path from a peptide to a protein is as long as the path from a brick to a cathedral. And, generally speaking, no sweeping conclusions are being drawn here. What we're seeing is this important detail, that these building blocks of life can form without water. They can, and in the process, they might even create water. If there was no water where they appear, then it's entirely possible to imagine a scientific scenario, a hypothesis that the building blocks for future life arose, for example, before the formation of planets. Just as the planets themselves appeared places where life could take hold. Now, these amino acids are searching for their ancestors in space. Rockets are launched. Probes peer through telescopes. Scientists have now published the largest and most accurate 3D map of the early universe ever created. And what's remarkable is how it came together. They built it using data that was essentially discarded from another large-scale study. The original project was designed to investigate dark energy, and for that purpose, only about 1 in every 20 frames from the full dataset was actually used. These were images of the night sky captured by a ground-based observatory across multiple wavelengths, forming a map of millions of bright galaxies. In the end, only around 5% of the data served its original purpose. The rest was left unused, until now. Because the authors of this new study realized that this unused data could be transformed into an entirely different map for entirely different goals, one that turned out to be no less powerful and no less valuable. We can see the result of their work, as the researchers themselves explain. The faint hydrogen radiation that permeated the universe 11 billion years ago. The hydrogen glows here because young, hot stars bombarded with ultraviolet radiation, causing the atoms to emit a characteristic signal in response. Scientists call this Lyman alpha radiation, a kind of cosmic marker, revealing where stellar life is actively forming and evolving. The problem with earlier maps was their limitation. They could only detect the brightest sources of this glow, the massive galaxies, while everything else remained hidden. The gas between them, the dwarf systems, the diffuse intergalactic matter. But what others dismissed as noise, the researchers saw as opportunity. They took that overlooked signal and transformed it into a powerful scientific tool, unlocking a layer of the universe that had, until now, remained invisible. Another shot. Look at this devilishly beautiful sight captured from aboard the ISS. It's simply impossible to do this from Earth. The red sprite flashed by for just 10 milliseconds, and the astronauts managed to catch it on camera. It hovered above the thunderstorm, which was raging below near the Earth's surface at the time. The sprite itself is born in the mesosphere at an altitude of 40 to 80 kilometers. It doesn't strike upward or downward like lightning, although the photo makes it look like some kind of discharge. It flashes like a light bulb, but a very powerful one. Such a flash is enough to disrupt the lower edge of the ionosphere for hundreds of kilometers around. And this is the layer that reflects shortwave radio signals and enables long-distance communication. Communication disruptions can occur in this layer. In the area where the sprite flared up, each such flash also mixes the chemistry between atmospheric layers, affecting the ozone layer and the planet's radiation balance. We don't yet fully understand exactly how this works. That's why scientists love getting such unique images. Red sprites are extremely rare, and it's even rarer to get such a clear view of one. It might be possible to see the recently discovered comet from Earth without a telescope as early as the beginning of April, if it survives its close approach to the Sun. It was only discovered in January, and it immediately became clear that it was a comet, not an alien spaceship. But that doesn't make it any less interesting. It's exceptionally bright, having become 600 times brighter in just a couple of months. Such flares are rare among comets. The last time was Comet Lovejoy in 2011. They rarely survive their closest approach to the Sun, but it does happen. They usually break apart under the influence of tidal forces or simply evaporate. But they can blaze across the sky, comparable in brightness to Venus. If you decide to observe it yourself, try doing so on April 4. That's when it will reach peak brightness, but it will be right next to the Sun's disk. So you'll need to shield your eyes with your hand or a piece of paper. But if you don't want to leave the house, or if the sky isn't clear where you live, the Soho Observatory's online broadcast will come to the rescue. Scientists will start pointing a telescope at the comet as early as April 2, and you'll be able to watch along with them online. And the major events we've been waiting for, first in February, then in March, and now in April. Let's see if they'll be postponed again. The launch of humans to the moon. For the first time in half a century. Without a landing, of course. That was already postponed back in the 1930s. For now, it's just a flyby. They're postponing it due to technical issues with the rocket. Strange behavior of the heat shield, then a hydrogen leak at the launch complex. But that's all normal for such complex and large-scale programs. The main thing is that they're not canceling it, which means the launch will happen. A historic event. This is exactly what our era will be remembered for, and we are living through it. A rare occasion to rejoice and take pride as humanity. Thank you, friends.